Hello again, everybody, and welcome back. This is our continuation of example 4-1. In fact, I should probably write that at the top right here. Example 4-1. And so we're talking about projectile motion, and we have a zero launch angle. And if you recall from the first part, so this is continued. Oops. Continued. From the first part, we had a skateboarder who was rolling along. All right, there's a skateboard right there. And they have a ball in their hand. And the whole skateboard system, including the ball, is moving at a velocity of 1.30 meters per second. And the ball, which is in the skateboarder's hand, is not thrown forward, but it is simply released. All right, and so since the ball has that initial velocity as well of 1.30 meters per second, it's going to continue moving in the horizontal. But not only that, it's also going to start moving in the vertical because, as we know, our old friend gravity is going to start pulling it downwards. And so it's going to give it kind of an arced trajectory. We saw in the last problem how it was displaced downwards in the y and to the right in the x, and it wound up over here, like that. And then as it continues, the ball is going to continue to be displaced downwards and downwards like that. And so it's going to have this sort of curved, arced trajectory. It's actually moving in the x and in the y. I realize we've talked about arced paths in 1D kinematics, but that was really the motion of an object with respect to time. Here, the object really is moving in the x and really is moving in the y. And so what we want to find out is, and I'm not sure where this is going to be exactly, let's just pretend it's right here. So right there, we want to find the final velocity at 0.5 seconds. All right, sorry that's so, I can't zoom in very well. 0.5 seconds. Okay, what's that going to be? Well, if you look at it right there, you can see that it's taking this path that's going sort of like that. And so it's going to be moving basically tangent to that arc right there. All right, to that path, that trajectory path. That's going to be the final velocity at 0.5 seconds, at one half second. Well, how do we find what that is? What we can do is we can take that velocity and we can determine it by determining its x component, v final in the x at 0.5 seconds, and its y component, v final in the y. All right, that's what part C of example 4.1 is asking. Find the velocity right here. Okay, that red arrow. Okay, how's the ball moving? Well, it's moving down and over a little bit. Originally just moving over, just moving in the x direction, right, when it was released by the skateboarder right there. But since gravity's kind of taken over, it has given the ball a y component as well as its original x component. So if we can find that, if we can find the v final in the y direction and in the x direction, we can put them together using trig and determine what this final velocity is in the, well, whatever direction it's going to be in right there. And we can determine that direction using what we know from trig and vectors. Okay? So I'm going to set up my table, my x and y table, over here to the right. So there's my x, here's my y. I'm going to draw my little dividing line down between them because they are independent of each other, with the exception of time. Time is the one thing that links them together, and that's going to be very important. By the way, why don't we just go ahead and write that first? Because we can say that the amount of time that elapsed, or we're told the amount of time that elapsed, time is 0.500 seconds. Okay? And the same thing for y as well. Time, I don't want to really put time in the x direction and time in the y direction, because time doesn't have any direction, but as it applies to x or as it applies to y, that time is going to be 0.500 seconds. Okay? So, let's write some things that we want to know. Well, first of all, we want to know the final velocity in the x equals question mark, and we want to find the final velocity in the y direction, which also equals question mark. That's our big question right there. If we find the final velocity in the x and final velocity in the y, we can assemble this total final velocity vector that the ball has after 0.5 seconds. All right, let's write what else we do know. Well, we know the initial velocity in the x direction, right? Initial velocity in the x direction is what? Oh, it's 1.3 meters per second, right? It's leaving the guy's hand going that fast in the x direction. That's going to be important. Meters per second. What's the initial velocity in the y direction? Initial velocity in the y direction. Well, you might say, well, maybe it doesn't have one. It does have, well, you're kind of right. There is a value, but the value is 0. Initially there is no y component right here. And so we can say the initial velocity in the y direction is 0 meters per second. Okay. Well, what else is going on? There's no acceleration in the x direction, right? So acceleration in the x direction equals 0 because there's nothing moving it forward, nothing accelerating it forward. But there is an acceleration in the y direction. Acceleration in the y direction, as we saw from free fall, is going to be negative 9.81 meters per second squared. All right. Do we have enough to solve for our final velocity in the x and the final velocity in the y? I think we do. We have 3 knowns on each side. We've got time, we've got initial velocity and acceleration right here. All right, and so for v final in the x direction, for v final in the x, we can say that v final in the x equals v initial in the x plus acceleration in the x times time. Wait a minute, what's wrong here? Well, there's nothing wrong. We just did too much. The acceleration in the x direction is, of course, 0, right? Which is why, that looks like a 6, doesn't it? Which is why that whole thing usually gets dropped out anyway. So, there's no acceleration in the x direction. We can just say, oh, okay, we do know the final velocity in the x direction. That's the same thing as initial. V final in the x has to be 1.30 meters per second. Hey, that was easy. All right. Let's now find our final velocity in the y direction. Final velocity, oops, I should write 4. For final velocity in the y direction, comma. All right. Well, final velocity in the y equals initial velocity in the y, right, plus acceleration in the y direction, which we know, times time. Okay? Well, initial velocity in the y direction is 0, so that can go away. So we can say the final velocity in the y direction is simply acceleration in the y direction times time. What is our acceleration in the y direction? It's going to be negative 9.81 meters per second squared, and our time, of course, we're told is 0.500 seconds. You know what? I left the units out for the other one, so I'm going to leave the units out for time. Sorry, time. What does that wind up being for a final velocity in the y direction? Well, 0.5, I think that's going to be negative 4.9. Let's see, 4.9. We're going to round it to 4.91 meters per second. Okay? Final velocity in the y direction is going to be negative 4.91. Negative 4.91 meters per second. All right, so the initial velocity in the x is going to be the final velocity in the x. It's still moving in the same direction on the x-axis, but in the y direction, it started out with no y component, and all of a sudden now has a negative y component of negative 4.91 meters per second. So that's what we're told. So we're told that, so we know that at 5 seconds, the x velocity, v final in the x equals 1.3 meters per second, and the y component equals v final in the y equals negative 4.91 meters per second. So that means we should be able to reassemble or reconstruct the full final velocity at whatever angle it is at 0.5 seconds. How do we do that? We can do that with trig, right? With our Pythagorean theorem. This final velocity right here, this red arrow that I really buggered up here, this is going to be simply the Pythagorean theorem. So for final velocity in the whatever direction, just for final velocity, comma, there we go, we can say that v final equals the square root of what? Well, the x squared, the x value squared and the y value squared, right? 1.3 squared. I should write 1.30. 1.30 squared plus, what's the y? It's 4.91, right? 4.91 squared. I should put brackets around the first one as well. Now again, why did I not put negative 4.91? Well, we just want to get the magnitude. What we're really solving for here is the magnitude of this red vector, the red velocity vector that the ball has at 0.5 seconds. All right, let's find out what that final velocity is. Oops, I'm writing in green now. I don't want to do that. I want to write it back in red. Final velocity total, you might say. Oops, dropped my calculators. 1.3 squared plus 4.91 squared. And you'll notice I didn't put the negative in there because the negative is going to go away anyway. Take that to the 1/2 power, or the square root. That's going to be equal to 5.08. 5.08 meters per second. All right, that is going to be, let's dotted line box that, most of our final answer. All right, let's find now the angle. For the angle theta, we know how to find angles if we have the x and the y values, right? Theta is going to equal the inverse tangent of what over what? Oh, the y value over the x, right? So that's going to be, what's the y value? 4.91. And again, we can just use absolute values right here. We don't need to worry about signs. We're just getting kind of a reference angle over 1.30. And that's going to give us our angle theta that this ball has, kind of, or the direction that it has right at 0.5 seconds. All right, so what is the inverse tangent of the y value, 4.91, divided by the x value, 1.30? That's going to give us 75 degrees. 75 degrees. All right, so we have our reference angle. The question is, and by the way, so that 75 degrees is probably kind of hard to see right there, but right there, it's based off of the horizontal. Okay, so what direction is it going? What quadrant is it going? Going down this direction, it's going to be south of east, right? So south of east. Let's dot a line box that. And that's going to be very important to us because that's the other part of our final answer. So we can say finally that at t equals 0.500 seconds, comma, the final velocity is going to be 5.08 meters per second at 75 degrees south of east. That, my friends, you can box it up because that's what your final answer is going to be. And when you do problems like this, make sure you're specific enough as to indicate that that's your final answer as well. All right. So this is really just kinematics, right? But it's dealing with two directions. We've got a final velocity in the x, a final velocity in the y. And then we have, we have components that we can put back together to reassemble into a final velocity vector. So that's how fast and what direction it's moving at 0.5 seconds, and in a fraction of a second before or after that, it's going to be different. But right at that time, at 0.5 seconds, that's the final velocity. Okay? Now the original question asked, I said find the velocity and the speed as well. In this case, they're going to be the same thing. The speed is just an absolute value, or just you might say a scalar. So it's going to be 5.08 meters per second. But you will notice that our final velocity in the y was negative. But when we put it all back together into a full magnitude of that just v final, that it just became positive 5.08. It just became an absolute value. But the negative was indicated by the direction. It's south of east. It's below the positive x-axis, and that's where that y comes from. That's where that negative goes right there. So the negative didn't just go away, but the negative is included in the fact that this direction is south of east, or below the positive x-axis. All right. Well, thank you for following along on that one. That was the other part of example 4.1. I realize it took a little bit of time, but I want to make sure you understand it. So please let me know if you have any questions. And in the meantime, thanks for following along. I'll see you on the next one.